dimensions, and I want to talk about knots in 3 and 4 dimensions. And I guess the reason is, you know, if I want to tell you about how to visualize things in 4 dimensions, then we must visualize something. And a nice object to visualize is knots, right? Elephants simply don't live in 4 dimensions. Anyway, the strategy would be to learn how to visualize things in 3 dimensions, pretending we were living in 2, and then just raise it 1 dimension up. Okay? So here's an example. Here's an elephant in 3D over here, and upside down here. Well, you know, I don't know if it's 3D. It's actually still a 2D projection, but we're so used to interpreting these 2D projections as 3D that we actually almost think of it as 3D. So the point is to really understand the elephant flatly, and then raise that 1 dimension up, because I don't know how to raise this 1 dimension up. The elephant was complaining bitterly when I did this, by the way. Anyway, so here are a few things I could do. So I could project the elephant, basically put, well, they're more or less how I am projected on the screen right now. Okay? And maybe you can tell that it's an elephant, but you don't get much detail. I want something better. In fact, had you projected from the top, you would have thought it's a rabbit. And if you would had projected from the front, you would have thought it's a butterfly. I don't know what you would think it is, but not an elephant, okay? So here's something a bit more informative. So what I did is I put lots and lots and lots of dots on the elephant, but sort of enough so that you could still see through. And I colored the dots in colors proportional to their distance from me. So basically to the T coordinate, where T stands for temperature. So red means hot, meaning high in this 3rd coordinate, and blue means cold, meaning far away from me in this 3rd coordinate. And it might be hard to see it because you're sitting far and the dots may mix into each other, but if you look on the handout, and that's one reason why the handout is there, you may be able to see a little bit better. Anyway, the point is, okay, I can tell that the ears stand out to either side because there is a lot of red and lots of blue dots up there where the ears would be. Okay, I can tell that this elephant has nothing in its belly, because if you look in the middle, you see only 2 colors of dots, which are the yellowish and the bluish. So these are the one side of the belly and the other side of the belly, but there is nothing inside. Okay? And I could tell more by looking from the top. So from the top, before, I couldn't tell anything. Now I can tell that this elephant has 4 legs, and that the tips of the ears are really, really high up, and maybe I can tell a few more things. And likewise from here, I can tell that it has 4 legs, because, well, 1, 2, but in fact each one has 2 colors, so this is really made out of, depth-wise, 2 distinct things. And I can tell that it has a tail or a trunk? Trunk, because it's far away from me, and it's the same color as the tusks. Okay? So I can tell quite a lot from the elephant, on the elephant, using this thermographic projection, where you denote distances by temperature and temperature by color. And another thing that I could do is I could look at sections of the elephant. So this is a sideways section. If you compare it with the picture, where's my mouse? If you compare it with the picture here, this is projection on the green plane, and there is also projection on the red plane, and also projection on the blue plane over there. So this is not projection, section. So this is section through a green plane, this is section through a red plane, this is section through a blue plane, and in fact, each of these projections could have been seen as a movie of projections, and watching the movie, even though each frame of the movie is 2-dimensional, watching the movie allows you to completely reconstruct the elephant. So here is the green movie. So, oops, here it is. So ear, body, legs, another set of legs, body, ear. Okay? I guess I could pause it and do it frame by frame, and it's kind of fun to see how an elephant, but you know, maybe it's even more fun to do yet another one of the projections. So this is the red projection right now somewhere in the middle. And let's play it. So body, top, 4 legs, and sorry, I can't keep up. My language is not good enough. Legs, trunk, and tail. Well, it's kind of fun, isn't it? And maybe we'll do the last one. So the blue projection. So again, let me play it. So let's start from, oh, these are the tusks disappearing. Tail, body, first set of legs, second set of legs and ears, and then tusks finally disappearing once again. So they're way to the front. Okay, so now we fully understand elephants, and we can move on to knots. And I should say that many of the knot pictures that I will show you, especially the movies, were done together with Esther Dalvik, and here's a picture of her. So anyway, here is a knot. Okay, I think intuitively you know what a knot is. I will define it formally in a minute, but here's a picture. And then again, I can go through a straight projection which doesn't give me enough information because I don't know which strand went over which, right? I can look at a thermographic projection, and from this one I can actually completely reconstruct the knot, right? Because here, this is red, so it's above this, which is blue. Are you all with me? Is it clear? It should be, okay? And in fact, for knots, there is yet another type of way to convey the information, and it's called a broken curve diagram. So I draw the curve of the projection, but I break it wherever something is over something else. So if you want, technically, I could say that in the third coordinate, the t coordinate, which is of course temperature, where there is a gap, it means that the thing went below. So the picture is drawn at t equals 0, but where there is a gap, this path, this curve, went down to t is less than 0. So for a moment we don't see it. So is it clear that from this picture we can reconstruct our knot? Should be. Good. Oh, and here's the movie version. So a different way to say the movie version is to say, let us slice the knot on many, many different planes. So put it in space and slice it on many parallel planes. Basically, at t is constant for various t, or maybe it's y constant for various y, I'm not sure. And show the list of frames that you see. And what do you see? So at the bottom, you see a pair of points here, purple and purple, and green and green. These colors have nothing to do with the thermographic projections. They're only so that I can refer to the points by name. Okay? So a pair of purple points on the left, a pair of yellow points on the right. These are these two pairs. Then the points on the side stay stationary throughout. So the points on the side stay stationary throughout. But the points in the middle perform a nice dance around each other. So the points in the middle perform a nice dance around each other. And at the end, again, you have a pair at the top and a pair at the bottom. And that's the top frame. So is it clear? Let's watch the movie. We're not watching the movie. Why are we not watching the movie? Few downloads. Oh, sorry. Okay, here's the movie. So here's the knot, here are the frames, and here's the dance. So in principle, by watching this dance, you could have reconstructed the knot. And we're soon going to watch such dances one dimension up, and I'm sorry for the glitch. Formally, by the way, what's a knot? So formally, a knot is a closed curve in four-dimensional space. This is very handy. So here's a closed, sorry, in three-dimensional space, a closed, smooth curve, differentiable space in four-dimensional space. So this one doesn't want to close. Good. Except I consider two knots to be the same if I can reach from one to the other by a smooth deformation, a differentiable deformation, which stays within the space of closed curves in four-dimensional space. So this is a knot, but you know, this is the same knot because all I've done was to deform it more or less smoothly in three-dimensional space. Okay? Good. So now what would be a two-dimensional knot in R4? So a two-knot. So a two-knot will be a differentiable embedding of S1 stands for the circle, the one-dimensional circle. So instead the two-dimensional circle, meaning the sphere, inside R4. So a differentiable embedding of a sphere in R4. Modulo that I declare that two are the same if I can reach from one to the other by a deformation within the space of such things. So the formal definition, is it clear? I hope. So let's view a few pictures. Okay? So first of all, here is a picture and I think you fully understand it. It's a broken surface diagram instead of a broken curve diagram. What does it mean? It means you view it, well, it's projected to the plane, but we're so good at interpreting things as three-dimensional objects that we immediately see it as a three-dimensional object. As a three-dimensional object, it has some gaps in it. So here there is an annular hole. Here there is a gap. These gaps mean the surface, which we already understand, dips to t is less than 0 momentarily. Goes down to t is less than 0 momentarily, so it disappears. So now it's all clear, isn't it? So that's a two-dimensional knot in R4. Let's understand it a little bit better. Okay? So let's understand it starting from the bottom where there is nothing interesting to understand. Okay? So at the bottom, I see a tube. Can you see the tube down at the bottom? And this tube extends both to the left and to the right. Let's see what happens to this tube. Okay? So the tube goes to the left, bends up. The bends for a topologist doesn't mean anything, it's still a tube. Okay? So it's still a tube, and then the tube goes here, and it goes under something. Under what? At the moment I don't care, I'm just following the tube. So I just, you know, I walk on the tube and I know that up above me in some four-dimensional sense, there is something. Okay, at the moment I don't care what it is. Then I keep going and the tube expands to a big drum, and as it expands, it goes over something because that thing is cut. Again, so I look down and I see something, okay? But this is still a tube, right? It's just a thicker tube, so you know, if I were to draw it, maybe I would draw it a bit thicker, but who cares, it's still a tube. And then the tube continues going to the left, and then, sorry, now it's a drum, different word for a tube. But and then it closes up, and as it closes up, there is a gap in it, meaning something goes over it, okay? So it closes up, and things go over and below it, but it's still closed like that, okay? Now, let's go in the other direction. I hope this is long enough because it's lighter. So let's go in the other direction. It's a tube, a tube, a tube. It goes, what is it now? Under something. No, over something, because the other thing has a gap in it. So the tube goes over something, and then sort of expands and sort of opens up like a fountain. Okay, but it's still a tube. It's still sort of a tube, and which becomes a big drum. So basically it becomes a big tube here, and then something comes out of it from the side, namely the big drum. Oh, and the drum itself goes under where it had been before. Okay? But then something comes out of it to the right, and that thing is still a tube. And that tube goes over something, and then under something, and then it closes up, and as it closes up, it goes over something. But overall, it was just a tube that got closed. Okay? So, what is this? That's just a sphere, right? A tube that got capped on both ends is just a sphere. So for me, what I see here is a sphere placed in four-dimensional space in a crazy way, and it seems like that would be a knot. Okay? So before discussing on whether this is really a knot or not, let's look at a few more examples. So here's another one. By the way, this one and the previous one are by Carter and Saito, and there is a picture of them. I think there was a picture of them somewhere. Oh, we flew over it briefly. Okay? So here's another two knot. So again, I could go through the same description, and if you look at it, you'll realize that again, it's a two-dimensional sphere embedded in four-dimensional space, in R4. But this one is particularly stupid. Why? So let's look at various parts in it. So over here, the vertical tube cuts the horizontal tube. So the vertical part of our big sphere cuts the horizontal part of our big sphere twice. And in both places, it is above. Okay? Because the cut is in the horizontal. So the vertical is in both places above. So in fact, I could have thought of it as if the horizontal thing is simply below in a four-dimensional thing, sense throughout. So four-dimensionally, if you wish, this whole section is bluish, and this whole section here, the vertical, is reddish. But that means that they're completely unentangled. This is the parallel of having a situation like this. Okay? So I could just undo it. Okay? So I could remove this entire bend. But then I can keep looking. I could also hear these two, the horizontal here and the vertical here, really don't talk to each other. One is behind the other. There is no obstruction to moving them. And then here and here, in both cases, horizontal is above vertical. And again, so basically I could slide this whole horizontal thing out and above in a four-dimensional sense, in the T sense. And then I think this part, these two, would disappear. And you keep looking at it for a while, and you see that everything collapses. So in fact, this is up to a deformation, just an unknotted sphere. Up to moving things around, it's completely unknotted. I told you this was silly. Let's move on to a few more interesting ones. So here is one given by a thermographic projection, except you can't see the inside. So I've cut it in half like a shell, and this picture is where you can see stuff, but it really is half of that one. So what is this picture? Again, we have a long tube starting here, going around and back, and it's capped on both ends. So a tube capped on both ends is a sphere. And in 3 dimensions, it appears to self-intersect. So it's not an embedding, it's self-intersecting, right? Because here there is a self-intersection. But at the self-intersection, this is red and this is green. So on the fourth coordinate, red is above green, so there is no self-intersection here. Likewise, there is no self-intersection here, no self-intersection there. Well, the 4 potential self-intersections are not self-intersections. So this really is a sphere embedded in 4 dimensions. Can I undo it? So, okay, had this sort of thin tube in the middle been red throughout, I could have undone it. So if this was red, I could take this green cap and simply pull it out, right? But, but that's not the case. If I try to pull green out, somewhere by the intermediate value theorem, the shade of green along here would be the exact same shade of green as over there. And when I try to pull it out, they will clash. And when 2 points are at the same place in space and have the same color, it means that their fourth coordinate is also the same. So they are the same point, so that would be not an embedding. So as I try to pull this green out, there will be a clash. Okay? That doesn't prove that this is knotted. It only proves that, or it only shows that the naive way to unknot it fails. Are you with me? Good. By the way, here's the same thing as a broken surface diagram. So again, this one goes above that one, so there is a cut in the horizontal one. Here the vertical one is cut because in the previous picture here, oops, it was blue, and so now it's cut, and so on. Okay? And, by the way, maybe before continuing, I just want to show you that there are sort of basic ingredients, or there are some basic ingredients for knotting in 4 dimensions. So somehow, in 3 dimensions, you could argue that a single crossing is like the basic ingredient from which all knots are made. So here are a few basic ingredients, though not all knots are made of them, but still there are a few of the basic atomic knottings, if you wish. Okay? So one is this one over here, where, what happened to my good pointer here? So one is this one over here, where you have a thick blue tube. Here the colors don't indicate depth. It's just so that I can call the things by name. Okay? So this is a thick blue tube, and so this is just a broken surface diagram. And there is a thinner red tube that first goes over it. Like if I come from the bottom, it first goes over it because the cut is on the blue side, and then it exits on the other side below because the cut is on the red side. Okay? And by the way, I could represent the same thing as a movie. And the movie, so basically I could slice it in horizontal slices. Every time, well, when I slice these two things horizontally, you see simply 2 circles. And then these 2 circles come closer and closer to each other, and at some point they fly through each other. One flies through the other, and then they come apart on the other side. Unfortunately, I forgot to bring my, my demonstration circles. But basically, I have a movie in which 2 circles fly towards each other, and then one flies through the other and comes out on the other side. You are welcome to try to see why the 2 pictures are the same. But even before you do that, let me show you just a fun video from YouTube. So this is a diver. Can you see the diver over there? Lying flat on his back, or her back, I don't know, on the surface of some pool or whatever it is. And let's see what the diver does. The diver plays with 4-dimensional knot theory. Oops, let's get rid of the advertisement. Okay. Here's a diver making air bubbles while playing with 4-dimensional knot theory. Okay, sorry, that's just for fun. Okay, but you see, in 4D, there is yet another ingredient for knotting. And in fact, it's the ingredient that we saw before over here, basically here, the uninteresting ingredient. Sort of the two, if you wish, the two tubes trade places in a way that's not so interesting. Or if you want, the two rings fly, instead of through each other, they trade places by flying by each other, next to each other. So let's look at it. Where are we? Here. So let's look at it a little closer. So here is the movie. So this is the same picture as before. And then we'll go through a few legal deformation of it. So again, red here is on both sides above blue. And look at it, I can split them apart. Or, equally well, I could have split them apart the other way. Or, I think that's where the movie ends, but, right. Or I could simply cut red, so I could have, it could have been the reverse just as well. Okay? So, so these are the basic, or some basic knottings that you can have. And there is a funny thing here. And the funny thing is that these, you can denote these four-dimensional scenarios by completely two-dimensional pictures. So I could declare that when I write a two-dimensional crossing, so of course I can interpret it in 3D as being a crossing of two strands, of two wires, okay? But I can also interpret it in 4D as a crossing of two tubes. But then I did a notation for the less interesting kind of crossing. And for the less interesting kind of crossing, since, well, here there is a difference between the crossings. One goes through the other, okay? And here the two crossings play a symmetric role. Sorry, the two tubes play a symmetric role. So if I wanted a completely two-dimensional notation for it, it would be simply a crossing without declaring which one is above and which one is over. So now, with this sort of language, a picture like this denotes, so this is a picture made out of two real crossings, here and here, and one so-called virtual crossing right here between between blue and yellow. And this picture, well, doesn't quite still represent a knot, but it does represent a composition of three of the atoms that could later be assembled to be a knot. Okay? And in this case, if I wanted to view it as a movie, going from the bottom to the top, I would have three flying rings, right? Because each of these lines really represents a tube. And then in these three flying rings, the yellow ring flies to the right, the red ring flies in this way, the blue ring flies to the left. And as they fly, yellow flies through red, then yellow and blue interchange places externally, and finally red flies through blue. Okay, so that's a little movie that represents a certain four-dimensional knotting scenario. Let's watch it.
Lost the audio.
I have lost the audio. I haven't. I still have audio. I hear myself. This is on. Maybe the battery is out. Do you hear me in the back?
Yeah.
So maybe we should just stay with lost audio. Or if you want to replace the battery, I'll put it again after it's been replaced. Okay. Anyway, so let's watch the movie. Again, yellow through red. Then red and blue trade places externally, and then red through blue. Sorry, I think I messed up the colors at some point. But this is, again, this still represents some part of a two-dimensional knot in R4. So in fact, if I wanted to complete it, I would have to connect, say, this end to that end by a tube, and maybe this end to some other end by a tube, so that I get a complete two-dimensional knot in R4. Are you with me? Should I go faster? Okay. You see, I still have 29 minutes. That's a lot of time. But how do I know that a picture like this is really knotted? Intuitively, it's completely clear, but let me crush your intuition. Here are 3 pictures that, are they knotted or are they not knotted? How do you tell? So in fact, let's look at this one. So you look at this picture and you can stare at it for half an hour and you wouldn't be able to tell if it's knotted or not. So let's look at this movie by Rob Sherain. I don't know how to pronounce the name. Here it is. So we start from the same knot as on your handout, and we start deforming it. And, well, is it knotted or not? It's still hard to tell, isn't it? Knotted or not? I think now it's pretty clear that it's not knotted. Okay? So you see, right? Yeah, I think now it's very clear. So you see, and in fact, this is sort of the smallest of the 3 here. This one will take you even longer to digest, and there's no movie to help you. And this example by Haken is sort of designed to make it, in fact, very hard to tell for a machine, or even for a human, whether or not this is knotted. So, given these awful examples, how would you know, maybe I can take this one, hacken it, or dislocate it, or Sherain it, meaning deform it in such a way until it would look like the one on the right, and then undeform it in some crazy way until it would be the unknot. So why on earth would you be confident that this picture is at all knotted? So the answer is that we need a proof. And the proof has 2 parts, one that nobody likes but everybody knows, and then the second part knows to quote, and then a second part which I will do in more detail, because the first part I don't like either. So the first part is Reidemeister's theorem, which says the following. Well, the first part A of Reidemeister's theorem, is essentially what you already understood, okay? So every knot has a broken surface diagram, broken curve diagram. So any knot in the world you can represent using a broken curve diagram. Basically, it's a theorem in analysis, right? Or in analysis. So if you have a smooth curve in R3, here is a smooth curve, closed smooth curve in R3. And you project it to the plane, for example, by looking at its shadow. Well, the projection could be messy, but you can always move it around a little bit so that at most 2 things will cross at any point, right? Like, I don't know if you can see, but there is a point there where 2 points, basically you can deform it if you make it generic enough, random enough. You can deform it so that at most 2 things will cross at any point in the projection, and then one is above and one is below, so you can use a broken curve diagram to represent this knot. And then the second part of the theorem says that any 2 knot diagrams representing the same knot differ. So 2 diagrams represent the same knot if and only if you can go from one to the other by a sequence of Reidemeister moves. where the Reidemeister moves are the following three moves. When you see a kink, you can undo it. When you see one strand going over another one in two places in the same senses next to each other, you can again undo it. And finally, what is this one? Maybe I'll, instead of explaining it, I'll redraw it in a nicer way. So basically it says, if you have a crossing and a third strand going underneath it on both sides, then you can slide this one to the other side so as to get this picture. And if you look carefully, the R3 written there is exactly the same as the way I wrote it here. So Reidemeister theorem says that you can get from any broken curve diagram that represents one knot, that represents a knot, to any other one that represents the same knot by a sequence of these moves. And the proof is again a proof, well, maybe analysis is not the right word, but it's some sort of differential geometry. Basically, you have a curve in space, you deform it, and you ask yourself, as you deform it, what are the things that could happen to the projection? And the answer is, locally, in small scale, these are the only things, interesting things that can happen. At the projection, either a kink could become undone, or this or that. And then the proof is essentially an infinitesimal proof. You subdivide the motion into many small parts, and in each small part either nothing happens or generically only one thing happens, and only these things can happen. Okay? So sort of basically you have turned the global problem into a local one, in which all you have to do, or into a combinatorial one, in which all you have to do is to show that you cannot reach from this complicated picture to this picture by a sequence of these moves. But we still have the global problem to solve, namely, why is this combinatorially true? Namely, why is it that we can't, that using a finite sequence of such moves, we cannot go from the trefoil, the knot I've shown before, to the unknot. And the proof, or one proof, goes by defining knot invariants. So a knot invariant is something that you can easily compute from a broken curve diagram, some number or polynomial or something like that, that you can easily compute from a broken curve diagram, and that does not change under these Reidemeister moves. So if you have a big sequence of Reidemeister moves, it has to be the same as at the beginning as at the end. And if it is not the same, the two things cannot be equivalent. Okay? So let me give you an example. The simplest example I'm aware of. So the number of three colorings, or legal three colorings, of a broken curve diagram is a knot invariant. So what's a legal three coloring? A legal three coloring of a broken curve diagram is, well, you color the unbroken curves. So you color the unbroken arcs. So this one is one color, this one is another color. You color them in three colors, red, green, blue, say. And the rule is that at every crossing, so in every crossing, three different arcs participate. Well, in principle, kind of there are four sides to a crossing, but one of them is unbroken, so it has to stay in the same color. So in every crossing there are three arcs. And the rule is that these three arcs either have to be all of the same color, or all three colors have to participate, but what is not allowed is to have just two colors in one crossing. So lambda of a broken curve diagram, lambda of k, will be the number of 3 colorings that this broken curve diagram has. Okay? So let's check it. So lambda of the unknotted circle is 3 because basically it has only one arc in it. You have to color it red, green, or blue, and then you're done. However, lambda of the trefoil knot, so here is a picture of the trefoil knot, and here is another one, is 9. Why? Because, well, basically you color this one whatever you want, and that one whatever you want. Let's say I've colored them blue and green. Since on this crossing you already have green and blue, this one must be colored red. So, so you can color these two whichever way you want, and then the color of this one is determined, and you can check that the other 2 crossings will automatically, in fact the picture shows that, will automatically be legal. So I can choose this one to be whatever I want, I can choose this one to be whatever I want, and I'm done. And therefore there are 9 3 colorings of the trefoil knot. 9 is not equal to 3, so if I will show that the number of 3 colorings does not change under Reidemeister moves, I will know definitely that the unknot is not a trefoil, and therefore you cannot sort of haken it or tisselthwaite one side and then unhaken it in the other side and get from one side to the other. Okay? So I still have to show you that the number of 3 colorings does not change under Reidemeister moves. But that's not very hard. You see, so for the Reidemeister 1 move, if this one, okay, how do I do that? The point is I try to do it locally. So I want to show that the number of 3 colorings does not change when I make a move. So what I do is I say, let's do this move inside this circle. So inside this circle we do a Reidemeister move. And outside the circle the knot continues in some crazy way. I don't know how, I don't care how. So what I want to do is to show you that without changing the colors outside, I can perform the Reidemeister moves on the colored inside. So I want to show that I can, so basically, if you look at the picture before the Reidemeister move and after the Reidemeister move, then the number of colorings inside is the same, again, before the move and after the move, even if I don't change the colors on the boundary, because the boundaries will interact with the rest of the knot and I don't want to even think of the rest of the knot. Okay, so that's what I want to do. And it's kind of easy. So for Reidemeister 1, if the boundary was colored red, I cannot change it. Okay? So it goes as thread through, and since this is a self-intersection of an arc with itself, it can only have, well, this color will be the same as that one, so that one must be the same. So the other end must be red too. And then in the other side of the Reidemeister 1 move, if the bottom is red, the top is also red. So in both cases, there is only one possible way to color the inside. Now, for Reidemeister 2, so there are a few possibilities to check, but you know, suppose the bottom was colored red and green, then on the easy side of the Reidemeister 2 move, the top would also be colored red and green, and there would be only one way to complete the coloring on the inside. Right? Everything has to stay the same. On the left-hand side, since this one is red and this one is green, this one has to be blue, this one stays red throughout, so this one is blue, so this one has to be green, and again the coloring was forced. So only one coloring throughout. And for Reidemeister 3, there are a few more possibilities to check, but here is the check of one of them. So if you start from blue, red, and blue, then at the top you'll have red, green, and blue, and this is forced, and there is only one way to go through it. Okay? So the number of 3 colorings cannot change as I do the Reidemeister move, so we have conclusively proven modulo the first part of modulo Reidemeister's theorem, which is in analysis. We have conclusively proven that the trefoil is indeed knotted. Are you still with me? Okay. You know, we did have the refreshments at the beginning, so there is really no reason to continue. So well, okay, you know what? Let's do the same in one dimension now. So, first of all, instead of Reidemeister theorem, it's called Roseman's theorem. And it has 2 parts, and the 2 parts, well, I think the first part is before Roseman, the second part is by Roseman. So, the claim is that every 2 knot can be represented as a broken surface diagram. So basically, if you have a surface in 4 dimensions and you project it to 3 dimensions, the only type of singularities that you can see, the only type of self-intersections in 3 dimensions that you can see are, well, 2 planes crossing each other, at least locally. 2 planes crossing each other, and then one is above the other. So green is above blue in this case. Or there is something that didn't occur 1 dimension down, and this is that 3 planes can intersect at a point. So here in the middle there is a point where the 3 planes intersect. And no small deformation of that, no rattling of that. So you see the argument in 1 dimension down for why everything has a broken curve diagram was that sort of if we had a funny projection, we would rattle it a bit and it would become unfunny. Okay? But 1 dimension up, if you have 3 planes intersecting, no matter how you rattle them, if you move blue a little bit up, if you move green a little bit to the side, red a little bit to the side, the triple point will remain. So I have to consider these triple points. And in this triple point, there are 3 planes intersecting, so one is above, one is in the middle, one is below. So in this case, red is above, so it goes through without cuts. Green is in the middle, so it has only 1 cut, and it cuts blue, so blue is sort of cut into 4 pieces. But it's again, you know, the cuts just indicate that blue is below in the 4th coordinate. And then there is a funny 3rd thing that can happen, which is a so-called branch point, and it's very hard to visualize. And it doesn't happen in 3D, and it doesn't happen for 1 knot. There is no analog thing for 1 knot. But what it is this picture. Clearly you can see it, right? I mean, it's a 3-dimensional thing which you clearly understand. And the colors indicate the 4th coordinate. And the red thing here goes over the blue thing here, so there is a cut in the blue thing. If you want a better way to see it, here's a better way to see it. So let me show it to you as a movie. So as a movie, let's do a movie sort of in the time coordinate. Let's turn the color coordinate to time. So if I look at purple, purple is just a straight line. And then blue is again a straight line. And then green is again a straight line. And then orange is again a straight line. And red is again a straight line. So I always just have straight lines. So as a movie, it will be a movie in which a straight line moves. How does it move? Well, it moves up, turns 90 degrees, and moves down. And of course, you can do it completely smoothly. It moves up, and as it turns, it moves down back again. So that's the funny thing. Oh, and then if you, well, that's this funny thing. You'll have to believe me that these are the only things that can happen. And then instead of 3 Reidemeister moves, there are 7 Roseman moves. And I guess these 3 involve these branch points, so let's not think about them too much, they're too hard. And the other ones are sort of understood, so are understandable. So the first one is kind of like Reidemeister 2. So Reidemeister 2 was, you know, if you had two things like that, you can pull them apart. So now it's if you have two cups or two hats going through each other, but at different three-dimensional heights. So one is at different four-dimensional heights, at different T. So one is red and one is blue, you can pull them apart. The other one I let you visualize, the last one I let the Rosman 5 I let you visualize, and Rosman 7 is sort of the other analog of Reidemeister 3, and it's this mess over here. But even this mess is understandable. So what do we have here? We have here three planes making a corner, meaning forget purple, and what you see is red, green, blue, and they are like the coordinate planes in R3. They make a corner. So I have these three planes making a corner, and of course red is above green, and green is above blue. I didn't make the cuts, but it should be understood from the colors. And then comes a fourth plane going diagonally and flies through that corner all the way below it. This is purple. Okay? So at least it's clear why the two sides are the same in 4 dimensions. 1 dimension up, you could have gotten from here to here simply by flying purple diagonally downwards, and it's always below, so it never intersects anything. And then Roseman's claim is that that's all. And then the other claim is that the 3 coloring invariant of before still makes sense and is still an invariant. So again, okay, but what I color now is the patches of surface. So instead of coloring arcs, I'll color unbroken patches of surface, and the rule would be that whenever I have a singular line, well, around the singular line, there are 3 pieces of surface. The one that goes through and the 2 sides. And these 3 should be colored by either just 1 color or 3 colors. So the 2 legal colorings of a singularity like that are either all red or red, green, blue. Okay? And also here in these pictures, the colors no longer indicate depth. So you know, that's why I need more than one way to view things. Because now the colors indicate just this auxiliary coloring, the coloring that I'm counting. So if you look at the triple point, in order for everything around it, so for a triple point to be good, all the double lines that appear in it have to be good. So it turns out that there are about 5 ways to color it. So either all is red, or a configuration like this. And if you look at that configuration, again, every individual double line obeys the rules. So what was it, this one? So the vertical double line is monochromatic, and this horizontal double line is trichromatic, and this horizontal double line is also trichromatic. So everything, all the rules are obeyed. And likewise for all other possibilities. And in fact, the branch point in this particular instance is completely uncomplicated, because from the perspective of uncut surfaces or cut surfaces, this is simply a single surface, right? I could go from here to here by going around the hump, through the cut, and around the hump again. So this is all one surface with sort of a slit in it, but it's one surface. So if it's colored red here, it has to be colored red throughout. Then comes the hard part. The hard part is to show that if you go through this list of Rosman moves, then the coloring on the boundary determines the colors inside, and sort of the number of ways the outside can be continued to the inside is the same on the left and on the right of each Rosman group. Lots of possibilities to check, but it checks. So once you check it, the three coloring invariant is really an invariant and can be used to prove knottedness. So an unknotted sphere, I think this is an unknotted sphere, is made of uncut surfaces, so it can be colored 3 times. I mean, it has 3 ways, either red or green or blue. Now what about one of our proposed knots, this one? So let's look at it using a broken surface diagram. And unfortunately, I forgot to prepare it in advance, so let's slide there. So here is a broken surface diagram of that 2 knot. So you see, I claim that no matter how I cut, I color the left lobe and the right lobe. I can continue the coloring to the inside and in a unique way. So say this one was red and this one was blue. Then, well look, there is a small disc here in the middle. Right, you see this disc here? So there is a toroidal, an elliptical hole in the red, and inside it there is a small disc flying around, hovering around. So since this one was red and this one was blue, the disc must be green. And if you keep going through, so this one is blue still, and this one is red, so this sort of cylinder in the middle must be green too. So basically I can choose this to be whatever I want, I can choose this to be whatever I want, and the rest is determined, so the total number of colorings of this shape is 9. So this is not the same as that. Okay? And I have 2 minutes left, and I can either tell you, oh, by the way, sorry, I should have said that. There are many knots, not just 2. Basically, this coloring invariant is extremely insensitive. So it can detect the difference between a trefoil, between the first one and the second one here, but it cannot detect the difference between the second one and all the rest in this table. So you need something sharper. And in the 2 minutes, 1 minute that I have left, 2 minutes that I have left, I can either tell you about something sharper, namely there is something called the fundamental group, and here is how it is defined, and the fundamental group is a much stronger invariant and it contains the previous invariant, as you can tell from this exercise. However, groups in themselves are not very computable. Sometimes it's very hard to tell if 2 groups are the same or not. So if you have an invariant with values in groups, it just means that you've shifted the problem to the domain of somebody else, somebody in algebra. So I could tell you a little bit more about the fundamental group, or instead I could tell you about the simplest open problem I know about this topic, and you know, it might even be one of the simplest open problems remaining in topology, or one where we actually have hope. So which one should I do? Open problem? Okay, here's the open problem. Good. So, you see, before I told you how you can interpret basically diagrams that have crossings and virtual crossings as knottings of tubes. So schematically it's shown here. So the thing in orange is not quite the tubes because I was too lazy to draw it too precisely, but you should sort of think of it as here are two tubes passing each other, non-interacting, like the virtual crossings before, and this is sort of the funny way for two tubes to pass each other with an interaction. So one goes over and then under the other. Okay? On one side over, on the other side under. So any picture like this, where you have a line starting at minus infinity and ending at plus infinity, and in between having ordinary crossings and virtual crossings, becomes a long tube. Instead of a sphere, it's just a sort of tube that starts at minus infinity and ends at plus infinity, and somewhere in the middle, sort of minus infinity of R4 at the infinite past, ends at the infinite future, and somewhere in between does crazy nothings. So here's an example. Okay? So the question is, so here's a conjecture. The conjecture is two such pictures represent the same knot, the same knotted tube, if and only if they differ by the Reidemeister moves of before and the following additional 5 moves. And it's kind of fun to visualize why these 5 moves actually hold. Why do they represent, why is the sort of collection of tubes represented here is the same as the collection of tubes represented here in 4 dimensions? And if I had time, which I don't, I would click here and then you'd see a movie explaining it. But instead, I will stop and tell you that this is an open problem. We don't know if this is the complete list of relations, and we really, really, really care. At least I really care. Okay? So here are some books on knot theory, and that's the normal way I talk propaganda. I'm only 2 minutes over time.
Are there any questions for the speaker? I want to see that last movie.
Yeah.
You know, after the end of the talk, the movies are for a fee. Sure, but you know, I can show it to you, but it's a bit. I'm not sure if it will go fast. It won't go. Okay, you know what? Here it is. So it's actually 3 projections of the same thing. Okay, from 3 different sides. Again, by Esther Galvit is this movie. So you see, this is a virtual crossing. The 2 tubes pass each other without interacting. And this is 1 tube that goes over 2 others. Is it? No. Yes. This is 1 tube that sort of goes over to 2 others. So this one goes through it, and this one goes through it. Okay? So if you want to compare it with the pictures, I think it's this move. So here is a non-interacting pair of tubes, and here is another tube that goes over both. Okay? So I claim this is the same as that. So let's watch the movie. Well, let's even do it frame by frame forward. So it's kind of, these are not hard movies. Here it is. You've just seen it. Okay? And again, of course, I can play it again and again and again. But basically, all such, the other few moves have similar, very quick movies to explain them. But that's the easy side. The hard side is to show that this is all, that there are no other relations. Yes?
I'll ask the obvious question. Well, 2 questions. What about embedding higher dimensional spheres in dimensions 2 higher?
Ellen,
What
are you here? it might have been him. It might have been him who once told me. Oh no, maybe it was Mike Hutchins. No, Mike Larson. Sorry, somebody, a good juggler, once told me when I learned to juggle 3 things, never learn to juggle 4, because everybody will ask you if you know how to juggle 5.
You can juggle a Taurus embedded in 4th thing.
So, anyway, the answer is yes, there is stuff to say about 2 dimensions in 5, 3 dimensions in 5, 3 dimensions in 6, all sorts of things. People study this. The farther you go from, like juggling, you know, when you juggle 3 balls, somehow the emphasis is on doing better and better tricks. Okay? Or alternatively, you know, when you play the piano, it's so easy to make a sound that you should play it well. Whereas playing a tuba is so much harder that, you know, you just making the sound, you get credit. So likewise, the higher the dimension it is, you get the credit just for finding a knot. And in 3 dimensions, the questions become more and more intricate. I hope I didn't insult anybody. I don't think there is an insult here. This is the reality of life. In piano, anybody can punch, and it's not music. In tuba, it's also just making the sound is hard. It's not music, but it's still hard.